Thank you for joining the hands-on workshop, Performance Optimization for Intel Xeon Phi processors. This is episode 5. I am Andrei Vladimirov with Colfax International. In this episode we will talk about clustering modes for cache operation in Intel Xeon Phi processors of the second generation. If you boot your system based on a Knights Landing processor and enter the BIOS settings, you will see several modes for cache operation. They include all-to-all, quadrant, hemisphere, SNC4 and SNC2. Potentially, these modes can accelerate the performance of your application by shortening the latency of cache hits and cache misses and improving your bandwidth. But to understand which mode works best for your application and how you should address this in your code, it is useful to understand what these clustering modes do. The reason why these modes exist is that Knights Landing is a very complicated chip. It has up to 72 cores. They are organized into 36 tiles, and each tile has its own slice of the level 2 cache. To keep track of which memory address is stored into what slice of the level 2 cache, you need a tag directory. And to serve this huge number of tiles, the directory is designed as distributed. This allows you to parallelize queries to that directory. The way it works is that when a core needs a memory address, it will use a hash function to determine which tile knows about the state of this cache line. So there will be a request, tag directory, tell me which core has this data in the level 2 cache. The tag directory might say, well, core such and such has it in the level 2 cache, and forward the request, and the requested data will be sent to the requesting core. Or the tag directory may say, this data is not cached, so it has to forward the request to memory, and then memory will return the data to the requesting core. If you set your clustering mode to all-to-all, there is going to be no affinity between the tag directory and memory. And this is bad, because you can have these very long round-trip paths that I've just drawn. So the rule of thumb for using the all-to-all mode is basically never use it. The reason why this mode exists is just debugging purposes. As the programmer, you will be more interested in the quadrant mode, or the hemisphere mode, or potentially in the SNC modes. Quadrant and hemisphere are safe defaults. So if you don't know which mode to use the quadrant mode. In this mode, there is going to be affinity between the tag directory and memory. It means that if some cache line is served by this memory quadrant, information about it will be stored in a local tag directory. So when you have a request and there is a cache miss, the lookup in memory is going to be short. And this is better than traveling across the entire chip for memory. As the programmer, you don't really need to do anything in your application to take advantage of it, other than just maintaining data access locality. Also, you actually cannot do anything for it because the partitioning of the chip into quadrants is not visible in the operating system. So the procedure is basically set the quadrant mode and allow the chip to figure this out. But you can go one step further and accelerate not only the latency of cache misses, but also accelerate the latency of cache hits by making sure that you have affinity between memory, tag directory, and the tiles themselves. And this is available in the SNC4 and SNC2 modes. SNC4 partitions the chip into 4 parts, SNC2 into 2 parts, but there is affinity between memory, tiles, and the tag directory. Importantly, these 4 parts are exposed in the operating system as NUMA nodes. So here's your NUMA node 0, 1, 2, and 3. In a way, this is similar to a 4-way system with Xeon processors, which is also a NUMA system. And the optimization strategies for it are going to be similar between the 4-way NUMA system and Knights Landing chip in the SNC4 mode. You have to realize, as the programmer, that to take advantage of this organization, you do have to modify your code to make it NUMA aware. Essentially, you have to orchestrate your parallelism in such a way that these tiles mostly work with local memory, and then automatically all the requests from tiles to other tiles for cached data or from tiles to the memory are going to be local, contained within that quadrant. At least if you contain most of the requests, that is good enough. This is easy to do if you can think of partitioning your application into 2 levels of parallelism. The outer level of parallelism scales across the 4 quadrants, and the inner level of parallelism scales across the cores within a quadrant. You can do it with OpenMP. OpenMP supports nested parallelism as long as you set OMP nested equals 1. So you will run one process, 4 threads in it to scale across quadrants, and inside of every thread there is going to be a parallel region to scale across the cores within the quadrant. But you will need to worry about affinity. This is going to be very important. We discussed this in great detail in the How series. Alternatively, you can use a hybrid approach where you use multiple processes with multi-threading inside, and it is convenient to do this using the MPI framework for scaling across multiple processes and the OpenMP framework for scaling across multiple threads. As long as you have a NUMA-aware MPI implementation, for example, Intel MPI is NUMA-aware. When you run 4 MPI processes per chip, the MPI library will try to pin them to the respective quadrants, so that threads working in this process only utilize local cores. The local cores allocate memory only to local memory controllers, and all of the requests for cached data are also contained within that NUMA node. This is what's going to give you the extra push that shortens not only the cache miss latency like in the quadrant mode, but also speeds up your cache hit latency, because all of your cache traffic is contained within each quadrant. We have a detailed description of the 3 clustering modes in this Colfax Research publication. This episode concludes part 1 of the workshop, and in episode 6 we will start the hands-on part, where I will run several demonstrations of performance optimization on Intel Xeon Phi processors.